Hello, welcome to another lesson. So Unit 7, Quality Control Charts. So we're going to be dealing with charts, like this one, which determine if a process is in control or out of control. So in engineering or manufacturing especially, quality control is super important so that any product you make or anything you produce will meet the needs of usually the consumer or the customer. So the proper use of quality control, the reasons we would want quality control to be high level, is it can improve productivity or improve quality, and it can also reduce the costs of an operation. So let's learn a little bit about it. So the quality control chart, like one of these, is a graph to use to monitor and improve the quality of a process over time. So we monitor things and we want to improve the quality of a process. And you might wonder what a process is. A process is any activity that takes inputs and creates a product from it. So, what would you use a quality control chart for? Well, you could measure how effective a process is. So it could be figuring out the weights of a cereal box, number of chocolates in a given thing of Smarties maybe, the volume of a bottle of water, or all sorts of things. But the whole reason why we use the chart is determine if it's in control or if there's a problem. So, if these were your commute times to work, for example, and then all of a sudden you had this giant, big length of time on your way to work, maybe you got a flat tire that day. But the whole idea is that we're going to be looking at the data and seeing where it lies relative to the center line, which is the average, and see maybe if there's some sort of problem there and figure out some rules for deciding if there's a problem or not. So the action you take to improve your process depends on the type of variation present. So variation comes from two sources, controlled and uncontrolled. So there's two causes for things to be varied, which is if it's in control or uncontrolled. So controlled variation is the variation that's always present. So you'll have, for example, you're taking some results and it's like, okay, it goes a little up and a little down over time, these measurements do, but they're still in control because nothing crazy is going on because it's consistent and it's predictable, which means that you're always going to expect some variation. So for example, in a controlled process, like maybe you're baking some bread, your thermostat on your oven might go up and down a little bit. So you're trying to be at 350 degrees, but maybe it's going down to 345 sometimes. Maybe it's going up to 350. But a little bit of variation is not a big deal. So, the temperatures could be going up and down just a little bit over time. Maybe this is the temperature of a day, okay? Or if you were injecting plastic for plastic toys, making plastic toys, maybe you have slight variations in the plastic from a supplier, which results in minor variations of the product strength. But that's no big deal. A little tiny bit of variation is normal and to be expected. The problem is when we have uncontrolled variation. So that's unpredictable and sporadic, uncontrollable, random. We're not really sure what is happening to the process to make it so uncontrolled. So for our baking bread example, that would be like maybe you open the oven door and the temperature suddenly dips really, really low. Well, that's a problem. Now your process is out of control. You're losing temperature. You're not going to be able to bake that bread. Okay, so you want to make sure that door's shut. Or for the toys example, the injection molding, if you change to a less reliable plastic supplier, for example, this will lead to a huge shift in the quality of the product, in the strength and the consistency of your final product. And so there's going to be a problem. In this particular example, we have, this might be your commute to work. So you're going to, for example, this person takes 20 minutes on one day, 26 or 27 minutes on another day, a little less, but every day, basically, they have the same amount of time they take to get to work, except for this day. So when you look at that chart, something crazy is going on. That's because on that day, they got a flat tire. Now, if you didn't know what the cause was, you would just see that spike. You would want to take a look at your results and figure out, what the heck was going on that day. And this can be extended to all sorts of things. Doctors filling prescriptions, how many prescriptions were filled out that day, or it could be any set of data. It doesn't really matter what the data is, but we can make these quality control charts for all sorts of things. So this is what our quality control charts look like. We haven't broken up the pieces yet, which means I haven't discussed, what a UCL and an LCL is yet, but that's okay. Let's see if we can understand what it means before we do the rules. So before learning the rules, do you think you could explain if this process is controlled or out of control? So take a moment, pause the video and see if you can figure this out. Is it in control or not? Well, based on the legend, it says that red dots are out of control. So we have lots of red dots here. This one, this one, this one. You can see where the red dots are. I think this process is probably out of control. Oops. So I'm going to say out of control because you got a lot of red dots going on. And it says, can you explain why? Well, we don't have a real strong argument as to why yet, but I could make a few observations here. I could say, well, this one's above this upper control limit is what this UCL is going to be called, and this one's below it. Maybe that's important. Or maybe there's something to be said about if you have this pattern here, which is sort of, which is sort of going up over time. Maybe that's important. So let's explore some reasons why a process might be out of control. And in order to explore what it means to be out of control, we need to have a few shared terminologies, or a few things need to be defined. So what are the principal features of a control chart? Well, first of all, we have the center line, which sometimes is a green line. That lies right at the center of all your charts. So you can look at all the charts, you'll always have a center line. That lies at the population mean. It normally appears as a solid line between the LCL and the UCL. Those are going to be explained in a second. And it represents the expected value of the process, also known as the target value. It's, for example, if you're making, you have a plant which is making boxes of Smarties, for example. Let's just say you want 30 candies to a box. Your target value, your mu, might be 30 Smarties. But then maybe some samples, like sample 1, maybe the average is 29, or sample 2, the average is 31. Well, you're still shooting for 30, but you might not get it every time. So we want, on average, to be close to that. So the second principal feature of a control chart are these lower and upper control limits, the LCL and the UCL. And what are they? Well, they're lines that lie at 3 sigma, or 3 standard deviations, above and below the mean. And we kind of have a formula for this. It looks like this. The mean plus or minus 3 standard deviations. So let's not forget that mu stands for standard deviations. And you can calculate that if you have your data. And it normally appears as a dotted line on the control chart. So we have our dotted lines. You can just take a look at this chart here now and sort of pick it all apart. You've got your process average, or your mean. So this is kind of your target value, or your mu line. Your upper control limit is your mu plus 3 standard deviations, or 3 sigma. Your lower control limit is your mean minus 3 standard deviations, or your sigma. And we can see that something weird's going on over here. That says it's out of control, and there's probably a special cause for that. All the stuff in between the upper and lower limits are called normal variation, regular fluctuations in the process. So let's dig in a bit deeper. The upper control limit, UCL, is the largest value you would expect from a process with a controlled variation. Similarly, or likewise, the LCL, the lower control limit, is the smallest value you would expect with control variation. So those are kind of our maximum points before any alarms are sounded. So by comparing current data to these lines, you can draw conclusions about whether the process variation is consistent, in control, or inconsistent, out of control, and is affected by special causes. So long story short, you know the target is in the center of this. That's what your sample means should be. And your maximum points, your mean plus 3 standard deviations one way, and your mean minus 3 standard deviations the other way. Anything above those lines is a problem. It's out of control, which means you want to go in there, figure out what the problem is, and fix it as soon as possible so that your process can get back to normal. So as long as all the points are within the limits, we can say it's in control. If it's not, it's out of control. So let's go one step further and talk about control chart trends, which is rules we can use to figure out if something is out of control. So there's 4 of them. The first one is called beyond limits. So if one or more of our points are beyond 3 sigma, then we definitely have it out of control. So this is the easiest one to use. You just take a look and see if, I'm gonna erase this. I don't want to erase. 1 second. Okay, sorry about that. That's the easiest one, the beyond limits, because it just tells us very simply, is it above or below the upper or lower limit? If it's beyond those points, we know that it's out of control, for sure, easy. Zone A means if 2 of 3 consecutive points lie outside the 2 sigma limits, or 2 standard deviations, we know that there's an issue. Zone B, 4 out of 5 consecutive points fall beyond the 1 sigma limits, or Zone C, 7 or more consecutive points, which means one after the other, by the way. Consecutive means one after the other. Or, in sequence on one side of the center line. So let's take a look at this. Look at our data. This looks okay. These are within the 1 sigma lines. This is above the 1 sigma line, but that's not a problem because we don't have 2 or 3. We actually need 4 or 5 on one side of the line. Over here, this is okay as well. These are all okay. They're no problem. This is 1 outside the 1 sigma line. No problem, no problem, no problem, no problem. This is in control. This process is in control, not a problem at all. Let's see if we can find some that are out of control. So first example, beyond limits. You have 1 point outside the UCL. So of course, this is pretty easy to see. This is outside the UCL. Look, this is our UCL line, our upper control limit. It's way beyond. So of course, it's got to be out of control. No question there. Zone A, so remember our rule for Zone A, 2 of 3 consecutive points lie outside the 2 sigma limits, but within the control limits. So our control limits seem to be mentioned here, our UCL and our LCL. They're within the limits, but let's just see what's going on here. It seems that these, are probably something to be worried about. You've got one that's in the 2 sigma, you've got another that's in the 2 sigma, and you've got one right at the center. 2 of the 3 consecutive points, 1, 2, 3 points. Let me just make this more clear. This could be our first consecutive point, our second consecutive point, and our third consecutive point. 2 of them are outside the 2 sigma limit. This one and this one. Those are both problem points because, for example, if this is our 3 sigma line, if this is 3 sigma, then this is probably 1 sigma and 2 sigma. We've got a problem, right? It's in between 2 and 3 sigmas. Those are problem areas. So you've got to take a look at that process, try to figure out why it's out of control, and then get it back into control as soon as possible. Example B, Zone B. Similar to the last situation, but we have 4 of 5 consecutive points falling beyond the 1 sigma limits, but still within the control limits. So I'm just going to label the 1 sigma limit. So this is the 1 sigma limit, the positive 1 sigma, negative 1 sigma. What's going on? We need 4 of 5 falling beyond that. Well, what falls beyond it? Let's follow the line. These are all within the limits, okay? These are okay. This falls beyond it, but it's okay because it's only one little point beyond the limit, not a big deal. What about this? That's within limits. This is beyond the limit, this is beyond the limit, this is beyond the limit, this is beyond the limit. These are bad, this is bad. 1, 2, 3, 4. That area there, that's 4 points, 4 pieces of data that are outside the limit. So it's probably out of control, and we need to go and figure out what's going on in that process so that we can fix it and get the process back to normal. Now, of course, looking at these charts right now, we can't go in and fix the process because we don't know what the data is. But if you're in charge of a system, you better be in charge of knowing what can go wrong and how to fix it. So in this case, definitely have outside the limits here. By the way, just as a reminder, these points of data they would be sample means. So you would take samples and you would get their means, just like in the last unit, and plot those averages and see, where your data sits, more or less. So one more example, zone C, I think we have this one and the next one actually. 10 consecutive points fall on one side of the center line. So, what does that mean? 10 consecutive points on one side. So 10 in a row that are on the wrong side. So these are okay. That's 2, 1, 2, 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, that's a problem. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, did I miss one? Yes, I did. Sorry about that. 4, 5, 6, 7, 8, 9, 10. So if 10 are on the other side, even though it's technically in control, and by that I mean it's not outside these points, not outside the alarm limits, the UCL and the LCO, there's still 10 on one side. Ten consecutive points, which means it's definitely out of control. You're going to want to figure out what's going on. Maybe if this was some process, the machine has been tilted sideways or something, and it's now shooting things in the wrong area. There's a million reasons why this could be. Or if this was a traffic information, suddenly it's taking much longer to get to work. Maybe there is construction going on, which is now making it very difficult to get to work on time. It really depends on the process, but hopefully you're thinking about how this could work. Finally, we have an example of in control. So let's go through our situations, wondering what our rules could be, right? So if you forget what the rules are, you've got your beyond limits, which is one or more points beyond the control limits. Are there any points outside the control limits? So beyond limits, no, we're good, not out of control. Zone A. What about zone A? So 2 or 3 consecutive points lying outside the 2 sigma limit. So first of all, where is the 2 sigma limit? Between 10 and 18 here. I guess it would be about right here and right here, just roughly. Those would be our 1 sigma and 2 sigma limits. Is there anything lying outside the 2 sigma limit? Just one. Just one right here. So it looks like we're okay on that. Our zone B, is there anything outside the 1 sigma limit? 4 out of 5 points on the 1 sigma limit. And I'll take a look. Nothing here. No. If you take a look at this more closely, you'll see that everything's kind of doing fine. And finally, our zone C, 7 or more consecutive points on one side of the center line, one after the other. No, we definitely don't have that. Okay, so on the previous slide, I actually said 10 consecutive points. I made a mistake on that. It's supposed to be just 7, so actually 10 is fine. Sorry, 7 would be bad. 7 or more is bad. Anything below 7 is okay. So this process is in control. So this is some practice. I recommend that you give this practice a shot using the rules that we've done already. I will go through this, but I recommend you pause the video and give this a shot on your own, okay? So let's get going. Practice. Determine if the process shown is in control or out of control. If it is out of control, explain why. So tell me which rule, which rule and why. You could probably circle it on the graph or something. Note that each chart has horizontal lines drawn at the mean plus 2 sigma, and the mean plus 3 sigma. So those are standard deviations. So example 1, or practice 1, a gear has been designed to have a diameter of 3 inches. The standard deviation of the process is 0.2 inches, and we have our situation here we need to try and figure out. So just looking at this, I'm going to go through my list. Do I have anything out of control? Right away, it's beyond our limits. So this is out of control. There's no question. And the reason is it's beyond our limits. We have one piece of data beyond our limits. That's enough to kind of shut the whole thing down and say, okay, what the heck's going on here? This gear, the average size for these gears for this set of observations is 4, almost 4. It's supposed to be 3. We got a problem. That's never going to fit in the machine. You know what I mean? Practice 2. A liquid dispensing machine has been designed to fill bottles with 1 liter of liquid. The standard deviation of the process is 0.1 liters. So 1 liter is okay, 1.1 liters is okay, 1.2 liters is okay. Anything more than 1.3 liters is not okay. And anything below 0.7 liters is not okay. So let's take a look at this and see what we got. So is anything beyond the limits, anything above this line or anything below this line? Well, no, we're perfectly fine. So we'll move on to zone A. Anything outside the 2 sigma limits? That dotted line, here's the 2 sigma. Nope, we're okay. Actually, 2. We have 2 points outside, so out of control. And why? We have 2 points. In this case, they're consecutive. 2 points outside the 2 sigma limits. That's bad. All right, out of control. We have 2 points that are outside the 2 sigma limits. This part up here actually would have been fine. And our third practice, an engine part has been designed to have a diameter of 55 millimeters. The standard deviation of the process is 0.001 millimeters. So very specific stuff. I mean, if you have an engine and you don't have the right size parts, your car is not working properly, okay, to put it simply. So let's make sure this process is very much in control. That would be a bad thing if it wasn't. So let's go through. Anything beyond the limits? Well, this is our upper control and this is our lower control. Looks perfectly fine to me. Do we have anything going on here? You know, any problem areas? To look at this, I would say, yeah, nothing outside the upper and lower control. Our zone A situation would be if we had 2 or 3 outside the 2 sigma limit, nothing outside of it. I don't even know if there's anything outside the 1 sigma limit here. For example, that would be about here. It looks like everything is pretty much according to plan. There's no sets of 7 consecutive points on one side or the other of the center line. To me, this process looks like it's nice and safely in control. So any variation for this situation would be controlled variation. So this is in control. It's not out of control, so we don't need to explain why. Basically, it doesn't break any of the rules that we have. Beyond limits, zone A, zone B, or zone C. So you don't need to memorize those limits right now. You can use your table to try and figure it out on the previous slides, and hopefully that'll help you understand it. But long story short, this process is in control, nothing to be worried about. So it's all well and good to be able to look at a chart and know if something is in control or out of control. That's obviously a useful skill and should serve you well if you ever have to deal with these limits. But you're also going to want to know how to calculate them. Thankfully, calculating them is not that big a task. So when sigma is known, when the standard deviation is known, it can be computed from, you know, past values from data that we've collected earlier. The upper control limit and lower control limit can be calculated as follows. So we sort of have 2 formulas. The UCL is the mean plus the 3 sigma, and the lower control limit is the mean minus 3 sigma, which we talked about before. So those are the upper and lower control limits. The mu being the population mean or the target value, and the sigma being the population standard deviation. So if you have your, you have your mu, your upper control limit, 3 standard deviations above it, that'll be your UCL, and your lower control limit, 3 standard deviations below that, that's your that's how you would set that up. And anything that lives above here, if you have some points of data that live up there or down here, that's not good. So that's your rule of thumb is that you always want to avoid those. So let's look at a fairly simple example to try and make sense of what we have been given in terms of our formulas and how we can do problems like this. So example, a production manager wants to monitor the mean weight of soap bars produced on the line. The target value of the weight of a single soap bar is 100 grams. So the target value, that's going to be important to think about. It is also known that an estimate of the standard deviation for a single soap bar is 5 grams. Daily samples of 9 bars are taken. So every time you take a sample on that day, I should say maybe you have a few days you're taking samples. daily samples would be you take 9 of the bars, you get their mean, and that will be the representative data for that day. So you take daily samples of 9 bars taken every day during a stable period of the process. For each sample, the weights are recorded and their mean is computed. So at what value would you place the center line for this control chart? So let's think about this. The center line is the same as thinking about the target value. And really it's just another way of saying that it's the mean. And the mean is mu. The mu must be 100 grams. So you could have just written mu equals 100, but it's a good idea to understand why, okay? Calculate the LCL and the UCL for this process. Well, a few things that we should note down. First of all, the mu, the mean, is 100 grams. And the standard deviation, which is going to be needed, is 5 grams. Okay, good enough. So one thing that's going to give us is 3 sigma. So 3 times 5, what is it? 3 times 5 gives 15 grams. So our 3 sigma, maybe I should write it down here, our 3 sigma, 3 times the standard deviation is 15 grams. So the LCL will be like this. We know it's the mu minus 3 standard deviations, which is going to be 100 minus 3 standard deviations. Well, it was 3 times 5, so minus 15. 100 minus 15 is 85 grams. So the lower control limit is 85 grams. Our upper control limit is mu plus 3 standard deviations, because the upper, remember, you're getting the bigger number. That's your mean plus 15, or 115 grams. So those are the only things it asked for. Anything above or below the upper or lower limits are going to be a problem. So it doesn't ask for a sketch, but just so we know, we have this 100 line that we're shooting for our samples. We've got our upper control limit. Upper control limit would be 115. We've got our lower control limit, which is 85. So if we have any samples that, for example, this could be our, let's just say these are our samples of the day, and we've got some crazy stuff going on here. Basically, at the end of the day, the problematic samples are the ones that live outside of this. Maybe this would be, 120 grams. That would be a big problem if you're trying to make soap that is 100 grams in size. Or anything below this, maybe this is like a 70-gram bar of soap. A consumer is going to be pretty upset if you're telling them that their soap bar is supposed to be 100 and they're getting a 70-gram bar of soap. And this can extend to any industry, right? If you're producing something that a consumer is going to buy, you want those to be within limits. Or, you look at your bag of chips and you're supposed to get, 100 grams of chips. And half your bag is air. And you've only got 50 grams of chips. Well, you have a problem, right? Some customer is going to be calling in and being upset. So, long story short, this is how you figure out if what you're producing is controlled, so the process is predictable and the variation is within acceptable values, or uncontrolled, which means that there's something wrong with the process and you've got to figure out how to fix it, or you're going to end up losing money, losing customers, or it could even be unsafe. All right, so that's how we deal with these examples.